Okay, I think we can start uh, by looking at this problem 341. Okay. So I have two early problems, but I think I will skip this part for a while, because most likely our problems on perhaps in the exams will be I think similar with this kind of question. So we have a two-segment steel rod. It has circular cross sections with different diameter. We have two elements, element 1 and 2. And we have the E, the modulus of elasticity. And the question, it has two questions. The first is the total elongations under the tensile load of 20 kilonewton. And the second question, if the same volume were to be made into rod of constant diameter and the same 2 meter length, what will be the elongations? So I think we can start by taking the first question. Basically, when we solve the elongation problem, we start doing this formulation. We can start to write this, the FLAE, which I think described very well within all the sections, right? So we have the length for element 1, length for element 2. So we could describe each element. And we need to describe the force. Maybe let me describe the equilibrium. Okay, so we can start by taking the equilibrium. So we can take the equilibrium. Let's say we start from element 2. We cut over this element 2. So this will be 20 or P. And we have a reaction force. Let's name it F2. And we know that it's basically equal to the 20 kilonewton. And then we can also take equilibrium for, we can cut on element 1. So we can have this is 2, this is 1, this is 2. This is also the same. Okay, this is just show you the steps for every procedure. We need to start with the equilibrium. So F1 also 20 kilonewton. Okay. And then we can find each one of them for elongations. The length is 1 meter, or because I would like to state in millimeter because of the gigapascal, so we can start to write this 1000 millimeter multiplied with 20 kilonewton. And then the diameter is also in millimeter, so pi over 4. Squared multiplied with 200 gigapascal is 200 kilonewton over millimeter squared. And this is gigapascal. Megapascal is Newton over millimeter squared. Okay. Gigapascal is just multiplied by thousands. So we get the elongation 1, which is 0.02829 millimeter oh wait, we need to multiply with 20 kilonewton. Let me check and calculate. This should be 0 0.565 millimeter. Same thing with this. But different diameter. This will be 1.273 millimeter. So total elongation is let's say E1 plus E2 is equal to 0.839 millimeter. Okay, or so the second question is asked if the same volume material were to be made into a rod of constant diameter. So we need to make a new rod which has the constant diameter, the same length, and the same elongations. Oh no, the question is asking the elongation of this rod. So this is A, for number A. So for number B, so it should be the same constructions. So now it becomes L plus L2, and then this is F, and this will be the area. I will take the same diameter. And then E. So now this will be 2000 millimeter, 20 kilonewton. Now this will be pi over 4. This will be 10 millimeter squared plus 15 millimeter squared, but divide by 2, as in finding the average of the diameter. And then 200 kilonewton over millimeter squared. And this will be equal to 1.567 millimeter. So elongation for B becomes 1.567. Okay, I think this is pretty much straightforward. Yeah, I think nothing need to be analyzed, like over analyzed. So basically we can get a straightforward conclusions, right? Okay. Okay, let me work on the other part of the question. I have a lot of practices, but I don't think it will sufficient for today and next week. So I hope I can wrap up and you can also try after the class, right? Okay, let me go over for other part of the questions. Okay, this kind of questions will be very similar, but it's more complex compared to the first one. I hope you can try this on your own. Let me, perhaps this one. Okay. This is quite similar to what we have in, I think, in the chapter 2, but now it is having some elongations. So the beam AB, it has weight 900 Newton, and it supports for the air conditioning unit, which is 4 kilonewton. So it's 4 kilonewton, but the beam itself is only 900. So it is supported by the rods 1 and 2. The diameter are the same. The length is also the same, 1.8 meter. They also made of the same steel, the same E. So imagine that there will be displacement between 1 and 2, so it's going down. Okay, so perhaps there will be some displacement here, which is described by this UA and UB. So we need to find these two displacement. So by taking, the first thing we can do is perhaps we find the equilibrium by drawing the diagram. So let's draw the beam AB. So this is A, and this is B, okay? And suppose that we have the weight, this is in the middle. Let's say this is WB 900, and this will be WA 4 kilonewton. And we have all the distance for each weight. And whenever we see this kind of situations, we know that this will be the equilibrium situations where you can use for the force or the moment, right? Okay. And then the rod 1 and 2, it will have the reaction force, which is described by this F. Let me describe this as F1 and F2. So we know all the quantity. So regardless, we can take the sigma moment with respect to A or B. Okay? We will get the same conclusions. We will get eventually we get F1 and F2. So first we can take the sigma moment with respect to A. Let's say this will be our positive value. So sigma moment with respect to A. So we have WA 1, or let me just use the 4 kilonewton and then 1.2 meter, right? And then we have 900 Newton and 1.8 meter. And then we have F2, or let me just equaling this on F2 multiply with 3.6 meter, right? So F2, after we complete this calculations, this will equal around 1.7, 8 Newton. And to solve for F1, we can use the sigma F. Or if you want to use the sigma moment for B, it's also okay. You will get the F1. Okay, it will be the same. But I will just use the sigma F. So F1 is 4 kilonewton plus 900 minus F2, or 1.78 kilonewton. Or perhaps let me write F1 plus F2 is WA plus WB. Okay. So F1 is 3.117 kilonewton. Now from these two, F1 and F2, we will get the elongations. And each one of elongations will be for displacement A and displacement B. So we can write UA will be equal to E1, F1, L1, A1, E1. And UB it's equal to E2, F2, L2, A2, E2. I think it's also straightforward, but it's more likely to combine with our previous example. So maybe if you remember some of the typical problems in chapter 2, it will comes around with some other additional questions. Okay, like this one. Okay, this one is basically using the same constructions problem in chapter 2, but with some additional context. So we just put everything into the equations. This will result in 0.357, and this will be this. So the key is to get the equilibrium correct. Okay, so still we need to make sure that our statics need to be perfect, okay, at the beginning. Okay. If not, then we are not able to compute the next part. Okay, so let me go for the next one. So I will start from very simple questions and then adding the context on chapter 2 with chapter 3 as a main point. And after this, let's see what we have. This is also a similar construction with chapter 2, which we can see from this distributions load, and then it actually has the same problem, but it has some displacement. You have different in displacement A and C, which you get the total of the force depends on the weight on the dispersion load, right? I will leave this for you for try at home, but I would like to focus here now in more chapter 3 problem. Okay. And you'll see that in the textbook they will use the same picture for several problems. Okay. And this is I would like to say conceptual problems which doesn't have any computations, but we will have expressions for the result. Okay. Of course, maybe in the exam I will provide all the informations, all the numbers. Okay, so the question is finding the axial stress and finding the displacement of joint B or UB. Okay, you can see the picture. We have the forces, external forces PB. It's applied symmetrically around the joint at B, so there will be some forces over there, which makes the element 1 will be elongated. And then because they both attach to the walls, then the element 2 will be reduced or have a reduction. Okay, we can start by taking the equilibrium, okay, as usual. So taking this cut at element 1, and then cut both sides. So I will have both reaction force. So this will be our PB. This is reaction force for element 1. This is reaction force for element 2. We get the idea that the F1 is equal F2 plus PB, or F1 minus F2 is equal PB, okay, from the equilibrium. No need for the moment because we have only the horizontal forces applied. So equilibrium done. So this is equilibrium. Next part is we can state the elongation formula. Okay, FLAE. And then another assumptions, or we call the compatibility equations. We'll be taking the elongation for element 1 plus elongation 2, this will be 0. So we can start taking the, we can directly write the elongation formula within this compatibility equation. So let's do that. So elongation 1 is F1 L1 A1 E1 plus F2 L2 . Now we can basically solve it, and we can substitute the F1 or F2, and then we can get from the PB connections, and we can get the F1 or F2 within this part. So let's say we can substitute the F1, okay? So F1 substituted to be F2 plus PB and let's say, because I think, because this is only an expressions, let's describe the F1 small f as L1 A1 E1 and F2 L2 A2 E2, okay, to make it easy to follow. Okay, we get F1 plus F2 equal minus PB F1. So F2 is minus PB F1 over F1 plus F2. With the same method, we get F1 would be F2 or PB F2 over F1 plus F2. Okay. Now from this F, we can get the stress. So sigma 1 so this will be PB F2 over F1 plus F2 multiply with 1 over A1, and sigma 2 And that's it for number A. Number B is the displacement. And then because we know that UB is basically just E1. So E1 we know from our elongation expression, F1. So we can write PB F2 F1 plus F2 multiplied with F1. Okay, that's it. Okay, this is only the expressions. Okay, if the questions having the number, then we can just compute, substitute by the numbers, and we have the result. Okay, but I hope every time we do this, okay, we always start with diagram, equilibrium, and then depends on the questions, we can start taking the compatibility equations first, or maybe writing down the elongation formula. Okay, now let me go through, perhaps, let me check. Okay, maybe to end the class for today, let me start with this problem. Okay, the rest of the problem we can start tackling perhaps next week. Okay, let's start 368. That is the steel pipe with outer diameter and inner diameter. So we have two diameters, and then we have the aluminum alloy for a three-segment system, and then it is welded to section A and D, which is attached to the wall. Okay, and then we know the compatibility equations. But then the aluminum rod is cooled down by some degree of Celsius. So we know that the delta T will be taking down minus 38 degrees Celsius. Only the aluminum. The steel, there is no change in temperature. And all the given informations, which is the diameter, the length, the E, and also the alpha, okay, the thermal expansion coefficient. So what we need now, we can, firstly, if you want to draw the diagram, I think it's okay. We can draw the diagram. Perhaps we can draw in the section B, because that is the one that has displacement, and also section C. So at joint B, we can see this is B, okay, and this is the aluminum. Suppose this is reaction on element 1, this is reaction force on element 2. Okay, this is at B. And then at C, we have okay, we have this F3 and F2. Okay, I think that's it. We can move for a while. We can start maybe compute the area. Let's say the area 1. It has two diameters, so we need to use these two diameters. So pi over 4 outer diameter minus inner diameter squared. This will be equal to more or less 829.38 millimeters squared. And then A2 this will be equal to A3 equal pi over 4. It will be d squared, or the 15 millimeter squared, around 176.71 millimeters squared. And then we can start by taking the compatibility equations. We have three elongations, which is E1 plus E2 plus E3, because we have three elements that is welded all together. Then this will be equal to 0. Okay, and for this type of questions, because we have some thermal expansions, or we have the change in temperature for the aluminum. So for the element one, there is nothing additional. For element 2 and 3, we need to add the thermal expansion effect. Okay, so suppose that we have F1, the small f. Suppose that this is the formulations. We can compute this first, so that we can just plug in the results. Okay, so we plug in all, and with all the information here, we can compute this f, which is around, perhaps there will be different in decimals, but it's okay. Okay, and then we can take for every part of the system. This will be equal to 1.051. Okay, so we have all the component force, or the F1. And the equilibrium says here, just to make note, that F1 is F2, F2 is F3. Which means that the F1 equal F2 equal F3. Okay, so we can write this as just F, okay, just to make it easy. So we have the compatibility, right? And we have the F. So based on there are some additional thermal expansion. So E1, there is nothing extended, so this will be just F1, capital F1. And E2, but plus some coefficient expansion, and then E3 also we have another. And notice that this additional thermal expansion, it can be positive, it can be negative. It depends on the situations. If it is increasing, it will expand it. It will be, when it's cooled, it will be negative. But I will just write plus. Okay. The negative will be depends on the delta T. Okay. So I will write the expression first to help you to analyze analytically. Okay. Okay, so then when we have this E, then we can get down to these expressions. So substitute all with the F. And this will be equal to 0. Now remember that the F1, F2, F3, they are all the same. And for the small f, we already compute on the left, so we can substitute directly. So let me write that's because of this, right? So we can write the f is f1 plus f2 plus f3 is equal negative I will write with a bracket to help and negative at the outside. All right, we have now f is negative okay. Now we can put everything into the equations, and then we can get result is, because eventually the thermal expansion is negative, we have negative will be a positive. This is around 5.34 kilonewton for the F, which means the stress, the axial stress will be F over A1, which we can see from our expressions here. This will be equal to 6.44 megapascal. Sigma 2, since the area is the same and F is the same, is also equal to sigma 3, which is F over A2 or A3, 30.261 MPa. Okay. Now, sometimes it is worth to remember how to convert the megapascal and gigapascal. Megapascal is Newton over millimeter squared. So if you prefer, you can compute first. If you see any meter, you can go to millimeter, because it will be best to convert into millimeter squared or millimeter if you have the megapascal. Or when you have gigapascal, it is actually kilonewton per millimeter squared. So it's best to pair the Newton with millimeter. Okay, it's help you to compute. Okay. Okay, I think that's it. So for today, it's just like an overview, the simple, straightforward questions on chapter 3. Hopefully, by next week we can get into the more related to the statically indeterminate equations like this, but with more context, and perhaps, yeah, I think we'll give more exercise. I think I have prepared within these notes, like this one, that one, and I think we can get into the rest of the question, and I can give you more for practice. Okay. So our quiz is next 2 weeks, right? So 21, right? 21. Or do you want earlier? No, right? Okay, 21. I think it's okay. Okay, I think that's for today's class. Any questions? I will put later in the exercise notes and adding other exercise as well.